Hello! So, I'm here to talk about something called a limit, as you may have read from the title of the video. Now, a limit is how you evaluate points on a function, not so much evaluate, but assume the value of, if you can't normally find the value of a point on a function. Now, let me give an example. So I have a graph here. And I'm going to graph f of x is equal to 1 over x. Now, we're probably familiar with this. This has what's called asymptotes. Basically, as x gets really large, the slope down here gets almost exactly to 0, and our y, or f of x, basically goes to 0, and as it gets really high, our x basically goes to 0. And these would be drawn with dotted lines all the way down, but there's a graph in the way, so we don't really care. Now then, what if we wanted to find the point when x was equal to 0? Well, how do we find that? If we plug it in, that makes it equal to 1 over 0 when x is equal to 0. So that doesn't make any sense, because we cannot divide by 0. That's somewhat silly. Now, so how would we find this point? Well, again, we can't really find the point, but we can make an assumption to what its value will be. Now, this is using something called a limit, and I'm going to introduce some notation here. So instead, we would take, to find that point, we take the limit, you write lim, as x goes to our desired value, 0, of f of x, which we know is equal to, in our case, of 1 over x, the limit. Now, a limit is basically thinking of what value does a function approach as the value you're looking at gets to the value you want it to be. So as x gets closer to 0, what does f of x get closer to? And that doesn't mean it will ever reach it, but what does it get closer to? Now, as x is smaller and smaller, let's think 1/2, this turns to 2. When this is 1,000th, this turns to 1,000. When it's 1,000,000th, it turns to 1,000,000. It's getting larger and larger as x is getting smaller. Proportion. Now, so what do we do here? Well, what value is this approaching? It's getting larger and larger and larger, and if it never stops getting large, it's approaching infinity. And we could say the same thing in the opposite scenario. The limit as x gets to infinity of 1 over x is equal to 0. Look, as x gets huge, this gets tiny, this fraction here, and so f of x gets closer and closer to 0. But limits aren't only good for evaluating points on asymptotes. They're also great for a different kind of thing called a discontinuity. So let's say we have a function here, and I'm going to introduce a couple kinds of discontinuities. So this is a kind of weird function, but it's the one we're working with. And this point is missing. This point is down here. Okay, this point is missing too. It's all the way down here, but it does connect to the rest of the function. Now, using a limit, let's say this is c. But f of c is not where f of c should be. It's down here. So, how do we find what this point would be? Well, we take the limit as x goes to c, and c, of our function of x, of f of x, which could be anything. And that is going to be equal to basically what f of c would be. Our, let's say, our function would be defined probably in a piecewise way, where it says that f of c is equal to something else. So I don't know, let's just call this prime f of c, whatever. It's the real f of c point. That's not really what matters though. Now, let's look at this other area here. So how do we define a limit here? because over here, the same value was approached on both directions. But over here, if you're going from the left up, you get to this value, and if you're going from the right back, you get to this value. So how do you determine what the limit is? Well, this is not this is not a limit. This is a different kind of limit. It's not a traditional limit. So instead, let's call this point M. You'd evaluate this as two different limits. So you'd say the limit as x approaches M, and what you do is do a little plus sign, like an exponent. And that means it's approaching from the right to the left of our f of x, and that's equal to this point here, f of m. Right? Now, we then define it by the other side. And guess what we're doing for the notation this time? Doing a negative from, basically, if this was at 0, it would be coming from the negative direction of f of x. And that's equal to, again, let's say the fake f of m. Let's say what that would be, prime f of m. I don't want to use f prime because we'll get to that later and it's something a bit different. I don't want to make any confusions. Alright, so limits can find values that are approached just by doing this. And all you need to do is plug in values closer and closer to the value you want into the function and see what the function's getting closer to. It's that easy. Now, I just want to give a couple examples. Oh, by the way, the jumping one that needed to be defined by two limits is called a jump discontinuity, while the other is called a removal discontinuity. But that doesn't matter that much. Now, let's think of another function, a function we actually can be familiar with, and we can get rid of c and m here for the time being. Let's say we have, this is f of x is equal to x squared. It's a simple exponential function. Now, what is the limit if it's continuous? The limit as x goes to, let's choose a value. How about 3? Just to show that it can be applied to continuous functions as well. It's kind of just another way of doing simple algebra, but with notation for exactly what you're doing. And that is equal to, if we plug it into the function, 9. Right? As x gets closer to 3, well, that's not right. 3, f of x gets closer and closer to 9, right? If you get close to 3, you get close to 9 by the exponential of what point you're close to. Is the difference in size between these two. Now, this can also be the case if we have a slightly different function, where this is not defined at 9, and we still want to approach at 3, but this is instead, let's say, 18. And this would be, it's equal to f of x, or it's equal to 18 if x is equal to 3, right? So if x is equal to anything but 3, it's x squared. If it's equal to 3, let's say, 6x, whatever. Now, it would be the same exact thing. What does this get close to? It gets to 9 if we ignore this piecewise bit here. Now, there's one other important definition of limits that I want to tell you about, and that's something called the Epsilon Delta definition of limits. And basically, it says that if we have a function here of some kind, let's say we have something here we care about. It doesn't matter where the other point is. Let's say it's down at negative infinity, whatever. And this is our c. And this is what we call up here the limit of c. Now, what the epsilon delta definition is telling us is that if we specify a range close to C, and this is the delta range. We draw a little delta here. Not sure if you can see that. And this is, well, this is of course C plus delta. That's our delta, and this is C minus delta. We will get, within a range, epsilon of L. So this is L minus epsilon, where epsilon is just this, and delta is just the Greek letters. And L plus epsilon. And basically, the equations in here are fairly simple. So if we take the absolute value of, what was it? X minus C, or C minus X, it's an absolute value, so it doesn't matter. It's going to be equal to, no, not equal to, geez. It's going to be less than delta if our X is in the specified range. And let's think, if our X is here, we subtract this value, we get a little value. That's less than delta. And similarly, absolute value of X, or C minus X, it doesn't matter how you do it. Oh, not X. F of X, our point up here, minus L, is less than epsilon. And this equation here can easily be turned into this equation by turning x into f of x, whatever the function is. You just put these through the function, and L, the distance L, specified range from our limit, the distance epsilon, I'm sorry, is going to be just kind of that, the same as delta, but a function of delta, the function of delta. And that's a basic introduction to limits. I hope you'd enjoyed. This will be very important in videos to come.